Good day. Today we're going to talk about the Chacon measure per second transformation on the unit interval. This is a very interesting transformation with properties that with very interesting properties, and the transformation was defined in the 1960s. This presentation assumed that you have viewed the definition of the Kakutani Neumann transformation that talked about cutting and stacking, the cutting and stacking process to define transformations. We're going to define this transformation also by cutting and stacking. So let me start by recalling the definition of the Kakutani Neumann transformation. If you recall, it was given by a sequence of columns. And we start with the base case, a column C0 that consisted in the unit interval 0, 1. Okay. And then we define a process where giving a column Cn, which consists of Hn levels, we say how to obtain level Hn plus 1. And in this case, let column Cn plus 1. And in this case, rather than drawing column Cn plus 1 again, what I'm going to draw is how we're going to draw what you can think of the process of how to go from Cn to Cn plus 1. So you cut each level in half, and then you send this level to the bottom right. So the top left is sent to the bottom right, and then you stack the right on top of the left, and that defines column Cn plus 1. And this picture gives us already the idea of the inductive construction. Okay? And that defines a transformation, the Kakutani Neumann transformation, that we're going to call T for now. Now, an interesting properties of this transformation, last time we saw that it is measure preserving and ergodic. What we're going to note now is that if you think about where this top level goes, okay, the top level eventually will go completely to the bottom level of the next column. Okay. So in particular, if we look at column C1, which we're going to draw here, column C1 will consist of the interval 0, half and a half 1. If we apply t to the top interval, if we apply t to a half 1, this will go to 0, half. Okay. So in particular, what that means is that if we apply t squared to 0, half, we obtain back 0, half. Okay. So we have constructed a set that is invariant for t squared, and that shows that t squared is not ergodic. Okay. Now the transformation that we're going to define is going to have all powers ergodic, and more than that, it will have the property of having t cross t ergodic. The Cartesian product of the transformation with itself is ergodic. It's a property that's called weakly mixing. So the Chacon transformation is an example, one of the earliest examples of a transformation that is weakly mixing and not in mixing. In fact, it is not mixing, a property that we will see is stronger than mixing. So this was just a quick review of the process of cutting and stacking that was used to define the Kakutani Neumann transformation. And here we observe that even though we proved, as we proved last time, that T is ergodic, the T square is not ergodic. Okay. So now we start the definition of the Chacon transformation. We start again with a column C0. So we start with C0. But in the Chacon transformation, C0 will consist of the interval 0 to 2/3. So it's not the full unit interval yet, even though in the end, the transformation will be defined on the complete unit interval. So we have C0 is not a complete unit interval. So now we are, in this case, going to give the inductive definition. So suppose we have a column Cn, which consists of Cn levels in the Chacon transformation. How do we go to Cn plus 1? In this particular case, we're going to cut each level into 3 sublevels, not 2 as before, but 3. But in addition to that, before stacking all the subcolumns, we will add what we call a spacer. We add a new level that hasn't been used yet. Where is it picked? It's picked from the outside the column Cn, and we will see in a moment that it will exist in the unit interval. And then we stack. Now we're ready to stack. So this goes here. This goes up into the new level that is called a spacer. And then this goes here, there. Okay. To clarify the construction, what we're going to do is here we will illustrate how to go from C0 to C1. So we'll draw C0 here. And note that C0 goes from 0 to 2/3. So you cut into 3 pieces. So this will be 2/9. This will be 0 to 2/9. This will be 4/9. And this one here is 6/9. So we add a spacer, which will be here. And the spacer will be a level of length 2/9. Where is it picked? It's picked to the right of 2/3. We haven't used anything. So we choose here of length 2/9 to the right of 2/3, the interval that goes from 2/3 to 2/3 plus 2/9. And we place this on top of that. And now the transformation is defined by sending this level here, this level up, and this level here. Okay? So if we want to look at the picture of, recall that we're showing here C0, we're going to construct C1 from C0. So if I show C1 here, C1 will consist of 4 levels. And we're going to draw the spacer there. There's the 4 levels. Okay, so that's C1. So height of C1 is H1, which is 4 in this case. Okay. So we will see that from here it follows that the height of Hn plus 1 is 3Hn plus 1. Okay. The height of C1. So this is creating, when we move up, we will see that it's creating a bump in the where the levels are going to go. Now here a point goes up, 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 and there. One can calculate that the mass or measure of the levels that are added. So let's see here. What we add? The first time we add something of length 2/9. The second time we add something that is a third of this, 2/27 plus that. And one can easily calculate that that sum will sum to 1/3. It's a geometric sum that sums to a third. So in the end, this defines a transformation in the unit interval. We have T. We will call this transformation that let's call it S here, not to confuse it with the T with the Chacon. Okay? So S is the Chacon transformation. And this transformation has the property that S cross S is ergodic. S cross S is ergodic. So this is a transformation defined, S is defined on the unit interval, S cross S is the Cartesian product defined on the unit square. So this would be a transformation defined on the unit square to itself with product Lebesgue measure. It has the property S cross S is ergodic. T doesn't have the property T cross T is ergodic. Because T square is not ergodic, one can easily prove that T cross T is not ergodic. Okay. So we have finished the definition of the Chacon transformation. Next time we will prove some of its properties. The next properties to prove next time are that it is weakly mixing, but not mixing. So let's just state those here. Properties S. So S is, of course, similar to the finite Neumann transformation, is measure preserving and ergodic. The argument that it is measure preserving and ergodic is similar, is essentially a very similar argument to the one we gave for the Chacon, for the Kakutani finite Neumann transformation. The new properties that we will prove is that S is weakly mixing, and this will be in a forthcoming presentation, will be weakly mixing, and S is not mixing. Well, thank you for today, so that we finished our definition of the Chacon transformation.